A single digital failure no longer stays contained. When a modern server rack overloads, it sends a rippling shockwave through the system, shattering the defenses of everything connected to it. Digital infrastructure has evolved into a web of dependencies, where the concept of an isolated threat no longer applies. Every node is now a potential gateway to the entire system. On the left is a linear model of risk progression, a chain of effects where one failure triggers the next in sequence. But the right side shows a modern network. A single compromised node instantly branches out, infecting dozens of interdependent systems. A microscopic error in a background update can generate a massive, disproportionate impact across an entire supply chain. Standard security frameworks are often overwhelmed by these nonlinear dynamics, as they were designed for a much more predictable environment. In 2024, a simple, faulty update from CrowdStrike, not a malicious attack, triggered this blue recovery error screen on kiosks and servers worldwide. Because the software was embedded so deeply into other systems, that tiny update bypassed isolated defenses, triggering collapses across commercial aviation, crippling international banking, and emergency healthcare. Malicious actors rely on these same interconnected supply chains, as seen in the 2020 SolarWinds hack. By compromising one trusted vendor's software update, hackers didn't need to breach individual perimeters. They used the vendor's own access to walk into the systems of thousands of downstream clients. To survive this level of interoperability, organizations must move beyond compliance checklists and adopt dynamic, AI-driven mental models to map these invisible vulnerabilities. Mapping a cascade failure starts with interdependency between systems. This creates shared vulnerabilities. When one node is compromised, the exploit travels the shared pathway, infecting others simultaneously. This initial failure is accelerated by feedback loops, as compromised nodes interact to intensify the damage. In many cases, these effects are delayed. The system appears stable to human operators, allowing the feedback loop to spin out of control. Eventually, the compounded errors hit a threshold and trigger a nonlinear effect, causing exponential propagation. Technological complexity acts as camouflage here, keeping these catastrophic vulnerabilities hidden until the exact moment of systemic collapse. This is an example of what Edward Tenner defines in his book, Why Things Bite Back, as the revenge effect. Tenner's premise is that attempts to manage our environment with advanced technology frequently result in unpredictable, countervailing risks. In enterprise cybersecurity, adding layers of defensive software actually increases the attack surface through added complexity, as each new tool requires integration and creates new pathways for failure. Our technological engineering has outpaced our cognitive ability to map the risks we have created, shifting the root cause of failure from machines to the humans who manage them. Systemic resilience is currently blocked by fragmentation within human organizational architecture. We call this the Tower of Babel effect. IT, legal, and business departments often lack a shared cybersecurity lexicon. They operate in silos, unable to communicate about these critical risks in a way that actually aligns with the technical reality of the network. This leads to a misalignment, where the rules meant to protect the company are disconnected from how the systems actually fail. Organizations rely on static directives like NIST-2 or ISO frameworks, but this often results in a checkbox compliance mentality. Managers fill out forms, while the network behind the clipboard begins to fracture. A network is only as secure as the human organization's ability to communicate. Without a shared narrative, the defense will fail. Solving these structural and communication failures requires an engineering approach known as adaptive network-oriented modeling. This is a computational shared mental model. It maps physical hardware alongside human organizational processes, linking things like learning and forgetting directly to the servers. The operational mechanism behind this is the use of continuous, AI-driven what-if scenario simulations. The AI fires theoretical attack vectors across the network to identify hidden feedback loops. When it finds a structural misalignment, the lattice reroutes its connections in real time to fortify the pathway. This allows the model to quantify the exact likelihood of a systemic failure before it occurs. This dynamic simulation replaces backward-looking compliance reports with continuous empirical threat intelligence. These AI models cannot rely on historical data alone. They demand real-time empirical data pipelines. The Cybersecurity Living Lab, or CSIL, provides the testing ground for this kind of data collection. The CSIL initiative embeds predictive analytics directly into a functioning security operations center, where analysts monitor the entire supply chain. Governing this initiative requires a quadruple helix framework, twisting together academia, industry, government, and society. These four sectors must co-design resilient security pathways to ensure that technical defenses and human policies stay in alignment. Mitigating Cascade risk effectively requires a cross-sector, collaborative, societal mandate. In a hyper-connected world, cyber strategy is business strategy. Organizations must transition from being passive victims of complex vulnerabilities to becoming masters of engineered predictive control.